psychoactivity conference of having the revered elders first thing in the morning so that we don't party too hard at night, or at least we don't get a chance to sleep off after having partied too hard at night. It's my honor and privilege to be able to present a man who really doesn't need any introduction, but that's an old cliche, and I'll give him a little one anyway. Sasha, or Alexander Shulgin, one of our esteemed and revered elders in this field, and a real pioneer in the structure-activity relationship studies of the alkaloids themselves, of the phenethylamines first and the tryptamine secondly. And this morning he's going to talk about the process of discovery and how it goes about that these things can be dreamed up or invented in the laboratory and become reality, as many of you may have seen or experienced directly last night. And of course, everybody knows that Ann Shulgin and Sasha Shulgin wrote P-Call something like 6 years ago, 5 years ago, 6 I think, and now T-Call, the long-awaited sequel, has come out, and these have really revolutionized the availability and accessibility of substances in the last couple of years, and they're having a really great impact, these books, far beyond what we've only seen the tip of the iceberg, really. And for me, it was really important because it was knowing that P-Call was going to come out. They published an excerpt in a magazine called the Whole Earth Review, and I hadn't seen the book, but just knowing that it was about to come out caused me to go back to publishing in this field, whereas I'd been doing it for some time, and I stopped because I was worried about attracting attention, legal problems. I was also dealing with my own career. And so it actually inspired me to start taking more of a political stand and speaking out and defending our political rights in this area. And I think that people focus a lot on the chemical and scientific importance of P-Call and T-Call, but their political importance is just as great and is really a valuable contribution. So on the process of discovery, please give a warm welcome to Dr. Alexander Shulgin.
I think I am, how do I say, ahoy, ahoy? Yeah, it works. It's always a little strange to be introduced as one of the elders. I guess I am. I'm kind of getting on in years. But internally, no one's an elder. Internally, everyone's kind of around 35 or so. And you remain being kind of 35, and slowly this doesn't work much anymore, and that doesn't work much anymore. Then you have to kind of slow down, then you get this replaced, and then you get that modified. Someone said the body sort of goes on its own way, but the pleasure is that the internal head stays around 35, and that, believe me, is a great blessing. I am going to try to give a talk in a different way today. I usually get involved, well, I think the best way of describing it, see, this allows me to prance. You can still hear me over here. Ah, good, okay. I'm sorry, that's problems for you, though. You have to keep, okay. The equation that is called research, investigation, discovering new things, experimentation, I would make up a slide, except I had some slide problems because I was using something for the transparencies last night that was slightly opaque, and I drew the transparencies out. I tried them out this morning. They were totally opaque, so I had nothing but black on the screen. So I was given very nicely something that was transparent, but I haven't tried them out yet, so this is still a mystery to be observed, which is, of course, what life is. Anyway, what I want to talk about is not what one finds out in the research area, but how one gets to finding things out in the research area. It's an unusual talk. I draw it up as an equation that A arrow B. A gives B. It's a very nice equation. It describes the research process, the investigatory process. You ask a question, that's the A. You scrape around in the lab or in the bottom of the barrel or in the library or something, that's the arrow, and you come up with the answer B. And so everyone says, gee, you have just solved a very interesting scientific problem, discovery. But the asking of the question is part of this process and is very often given short shrift because the answer is where you get your reward. So sometimes your question is modified by what answer you want to get to. And then you go back and find out what is a good question to ask. But either way, the process of getting there is often swept under the table, that arrow thing. For example, in academic research, there used to be always, you go to the universities back in the beginning of the century, early times, last century, beginning of this century, you went to the academic world because it provided a certain amount of stability, academic stability, a job, you could interact with students, you could teach, you could do research work, you're given a little laboratory, some funds came in from the university and you could stir something or react something or try hybridizing something as you wished. Your questions were of your own making. The funds came from the university and the answers were happily published in whatever journal were necessary to build up your bibliographic inventory sufficient that you could get tenure, and then you could either stop working or continue research at your own freedom. Unfortunately, in the academic world, this has changed more and more. More and more, the B has become the emphasis. Because over the last, I would say, perhaps 40 years, and recently almost totally disappeared, has been the academic sources of research funds. They say, oh, you want to do research, you want some graduate students, nice. Get a grant. Go out somewhere and find a source of funds. Find some industry that will give you a contract to do this work. We're not going to give you the money for it. Get the funds that will handle your students, will handle the postdocs, will do your research expenses. We'll take 30% of it for the janitorial needs and the keeping the garden green. But in general, the funds come from outside. So you get in a situation, this I have found more and more in the university, that the answer is dictated by the source of funds, and the source of funds is, in turn, what dictates the line of research. An example, I made this up, but it's the kind of thing you might encounter. You're curious. What is your question? What is the A of this A gives B? I have down here, does marijuana influence chromosome division? Now, there's a neat question. People are talking about marijuana is good, marijuana is bad, dangerous, not dangerous, innocuous, it should be, it should not be, this and that. Does it influence chromosome division? That's what you may want to ask for reasons of your own. But what you end up asking is, do marijuana users have excessive chromosome breaks? You're still looking at marijuana, you're still looking at chromosomes, buccal smears, few generations, look at them under a microscope running 1.8% breakage. And then you try to get people who have been smoking marijuana, maybe look at their smears, and maybe you find something in 2.2, maybe 1.6. You find 2.2, well, it's, as they would say, it is not statistically significant, but it's suggestive. I love the way you can euphemize these answers to maintain your grant renewal. So you get your grant, it is funded, and you end up, say, let's say, for example, in your academic world, you end up not finding significant amount of chromosome breaks. So you say, if yes, of course, you will say marijuana causes genetic damage. If no, you say no, chromosome damage was seen from marijuana use or associated with marijuana use. But the paper gets published in whatever journal it is you publish it in with keywords such as marijuana, genetic damage, chromosomes, reproduction risks. All these are pejorative terms that apply back to the paper even though the paper was a clean bill of health. So this is a form of very subtle psychologically influencing the granting agent in the U.S. government. The various governments love doing it as long as it applies. It's in some way the answers can apply to what their current political needs are. It's a sorry shift from the academic purity of research to the practicality of putting a dollar sign on that B of A gives B, and then working back from that to where the A is. Industry is not much cleaner. There used to be a term known as fundamental research. Sometimes it was called exploratory research. Go in the lab, putsy around, just have fun, and see anything comes up that would be of value. This is ideal. I mean, anyone would love this. This is the academic world of 75 years ago. Play around, enjoy exploring. Then more and more, the term I have heard used quite a bit, I think they're called bean counters. People in industry who look at the bottom line and see if this line of research is really economically valuable? Is there not another line that could be more efficiently followed? The people in the accounting office tend more and more to dictate the direction of research because they are the ones who will eventually have to pay out the check to the laborers, to the people, to the employees, and that check must come from the funds that come from the selling of a product that comes out of that research. For example, you might have a person in the research department talking to the accountant who says, you know, DuPont has just come up with a 7-fluorosteroid that is rather effective in treating something or other that steroids would be effective in treating. The answer is, well, let's get your research group working on 6 and 8 fluoro counterparts. They're patentable, and out of those we'll certainly find something that would be of value. So you have the dictation, again, of research by the bottom end, the B and its dollar sign. And this, you would think, would be totally absolved in the area of private research. And in principle, it is, and in practice, not quite. There are a number of institutions, number of groups in the area that we're interested here in the area of psychoactive drugs. You have the Hefter Foundation, you have the MAPS group, both of which have been very active in collecting, instituting, funding, and seeing research projects get initiated that are for the discovering of information about psychedelic drugs in general. But there's always this little smell of an agenda. Not to take any of the glory from any of these groups, the agenda is still there. Namely, we want to achieve these ends. You wish to achieve a certain amount of academic acceptability, a certain amount of social balance. These are all noble ends, but they are ends. And those ends in some way must be thought of by the person who's applying for a grant. Because he wants to get the grant is money, the grant will come from them, and I'll apply for it in a way that will give me a favorable review by the review board. Not much of an influence, but not totally without. So this area is, unfortunately, still smells a little bit of the A gives B, and the B is indeed the point from which the research starts. Anyway, with that, I want to get into a lecture and how I got into the area and what I want to talk about. But what I want to talk about is not the B, going this way, B. I want to talk about the arrow, but I'll tell how I got into it. I had worked first in industry about 1950-something or other, 55, 56. I went to Dow Chemical Company. I was never a total virgin in industry, in that kind of chemistry. Here's a big laboratory, big equipment, big instruments, anything you want to buy something, buy it, they'll buy it. And I thought, gee, this is marvelous, I can do whatever I want. Well, they don't quite let you do whatever you want. They say, here's what we're interested in working on. And I was introduced to my lab partner. He's a man who had been there a few years, Warren Kading, from which I learned a great deal. I learned this entire process of look at the arrow and not look at the bee. I learned it from him. He's a kind of a remarkable person. He is a person who I learned two things immediately. One, when he found something went strangely in the laboratory, he would say, that's utterly bizarre. He did not know that bizarre was pronounced bizarre, and he'd say bizarre. That's okay. The second one is one, I guess it's a little bit sexist, but I learned it from him, and it had its applicability. When something would really go wrong, he'd slam something on the floor. In fact, he kept a little line of broken beakers on the shelf. There's a wall at the end of the lab. And something went quite wrong, he'd pick up a beaker and throw it against the wall, smashing it. Well, the beaker's already been cracked, so it had no value. But just that throwing of the beaker, just marvelous. It expunged him of his anger. But as things went generally bad in a generic sense, he'd mumble, grumble, and say, chemistry is a woman. And we had a delightful, we both had technicians helping us, and they both were ladies. And somehow they got used to this from him, but it always struck me as a strange. Anyway, what he had, now here was my first experiment on transparent transparencies. Is this A-N-N? No. Yes. You're going to have to suffer dirty pictures. I call these dirty pictures because it always offends someone who thinks they're going to come up with pornography, but a lot of chemistry is pornography in disguise. You just have to know where to look for the functional group, so to speak. Anyway, this is industry. They had toluene, pennies a pound, and they could make benzoic acid for pennies a pound. And Warren Kading discovered that if you put benzoic acid, that's the thing that's up there that I can point. Well, I can point there. You can see it. The one up in the middle at the top. You put it in with copper salt, copper cupric this, copper that, and throw fire to it. It went into phenol. Well, Benzoic acid's pennies a pound, phenols many pennies a pound, and you go to 1 million tons, this is suddenly big money. And so that was his discovery. You could oxidize an acid to a phenol. Marvelous. So when I got there, he had explored the second line. They said, we need a lot of para T-butyl, that's a T-butyl group, that's CCH33 at the bottom. Para-T-butyl phenol, why not take para-T-butyltoluene, pennies a pound, oxidize it to para-T-butyl benzoic acid, and then oxidize it to para-T-butyl phenol. We'll not have a quiz on this later. This is just general information. He did it, and he came out with the wrong thing. He got meta. That group was in the wrong place. Well, the group didn't move, the phenol moved, but he worked that out later. So suddenly he got something that he was not assigned to get. It was the wrong thing. The boss said, wrong product, bad scene, try again. That's the mindset on the B and how you get there. Warren said, wrong product, good scene. What went wrong? And that, of course, is the heart of the arrow. What went wrong? And he fiddled around with it, and he found, by golly, it goes through a salicylic acid, decarboxylates here, and the phenol's over here, and it goes meta from para or whatever. Anyway, got the wrong thing. That thing is a virtually unknown compound. And that's when I came into the industrial scene, and that was available, and said, what you can do with it? Well, this I took as almost being a freelance offer, and I looked at that thing, I said, gee, that's got the same carbon skeleton as physostigmine. I drew down physostigmine down at the bottom here, and I guess I don't know, do I dare point? Yeah. Yeah, here's a methyl, there's a methyl, there's a methyl, there's a carbon, just as there is in here, methyl, 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 carbon, and there is an oxygen. So I bet, since the physostigmine is a real potent thing, and it's not that far from current insecticides, I'll wager you could take that T-butyl thing and put an amino group in the para position and make it dimethylate it, and maybe something, maybe a 3,5-dimethyl. I bet you get an insecticide. So I had the wit, the skill, the luck to get 6 signatures attesting for that as being a good idea. So I had witnesses to the idea. I made the compound, and it went commercial as an insecticide. And so, of course, the person who ran the insecticide lab, the person who ran that lab, my boss, everyone along the line tried to take all the credit for it, but I had 6 signatures that said I had thought it through and created it. I got the patent, and the people at the industry said, gee, if you have that kind of imagination that you can look at a structure and guess another structure that might be active, why don't you just do whatever you want to do? And I did. And it was about 5 years later, I left industry. Because what I wanted to do is nice, but not exactly what they wanted done. I got into the psychedelic drugs in spades. I began making all kinds of neat things. I sent them in for biological screening. None of them were particularly active, but they weren't looking for what I thought they had and what I then later knew they did have. And so I was published for about 2 years out of Dow. And then they said, we're not comfortable with your publishing with Dow's address in this area. I said, okay, I live on my own street up there. I'll publish from my home address. Said, fine. So for about 3 years, I published from my home address, and it was getting more and more uncomfortable. So I split the scene, left industry, went back to school, and then became a consultant and got into things that I truly have enjoyed, and that has been going ever since. So with this, I will now really start my lecture. Am I under time constraint? I am. No. I have drawn here 4 more dirty pictures, phenethylamine, PEA, and this shows the direction I really am now going with great interest. PEA can cyclize that little amino group, hang it down, bring it down, hang it down, and stick in something, and you come up with tetrahydroisoquinoline. The carbons are all there, plus 1 carbon. Where that carbon comes from becomes quite an interesting story. And so the PEA, and down here you have tryptamine, and tryptamine can do the same thing. Tryptamine has an amine hanging out there, which can duck around this way with a carbon and become tetrahydrobeta-carbolene. So there's a relationship between phenethylamines and tetrahydroisoquinolines, between tryptamines and tetrahydrobeta-carbolines. I have worked this trilogy quite thoroughly, and out of it, still things are coming. But the 4th entity is almost unknown up there. So I want to talk a little bit about substitute. Phenethylamine is not an active compound. I mean, it's in this, it's in that. I've taken it up to 1.5 grams, nothing. Perhaps if you took some other maybe things that would inhibit its oxidation or metabolism, it might be, but as it stands, no. You put stuff on that ring, and that's, of course, one of the main areas. Right up in here, Without getting too technical, we put a methoxy, monosubstitute, little odds and ends, up to about mono, and into the disubstitution you get stimulants, but they still decompose in the body quite rapidly. You get 2 or more than 2, you get psychedelics. You get up to about 4 and a half, I'd love to get half a group onto a ring. 4 or 5 on there, they begin losing all the activities, becoming inactive. So I played around in that area a great deal. The trimethoxy in that position with 3 methoxys around here was mescaline 1, 2, 3, is a compound mescaline, which is my first introduction into the entire area, personal introduction into the area of psychedelics. And I began making all kinds of modifications, put a methoxy here, up there, change them around, put a methyl group here, hang something on there, put a bromine in, put a methyl group, play around. And it's simple on the blackboard, and people say, well, it's easy to do on the blackboard. You get in the laboratory, it's more difficult. Sure, it's more difficult. Perfectly doable. Just be patient, sit around, find a way, you'll do it. And so this worked out gorgeously. And in general, I found that the 2 oxygens out here, like methylene dioxy, is not with a 2-carbon chain, 3-carbon chain, is MDA. That MDMA came from this whole route, which has that methylene doxy group on there. You can put methylene doxy in a methoxy, you get MMDA. These are things that come directly out of essential oils, such as L-amycin, myristicin, and such. And but more than that, mainly the focal point on this particular molecule is this 4 position. Where it is on that 4 position calls the type of action you get, but with something in the 4 position, you get activity. So it's really a beautiful thing. You take a salt shaker, put a little salt on there, you get this kind of a compound, put a little pepper on there, you get something else. Just modify that 4 position. With the tryptamine world, it was not quite as clean cut. Initially, then I began finding out, I'd look oxygen out here, that's, you have serotonin, you have psilocybin or psilocin, the oxygen up here, you have bufotenine as an oxygen unsubstituted out here. Okay, but the real power is what's on the nitrogen. So once I settled on a methoxy or an oxygen out that position, a dimethyl, diethyl, dipropyl, diisopropyl, methylpropyl, methyl isopropyl, on and on and on. The number of alkyl groups are unlimited, and the number of putting them on is unlimited, and the novelty, the treasure, the unique cascade of products that come out from it are absolutely joyful. Joyful to discover, to play with. Whether they have good actions or not, it's another question. But anyway, this is where the tryptamine is, but it's only monosubstituted. You make disubstituted tryptamine over there, activity goes. So again, the emphasis is some oxygen is good or can help, but the activity is on these 2 groups. In the tetrahydro beta carbolines, these are not as versatile and not as well explored. The one I really got in originally was harmaline itself, which has a double bond up in here and a methyl group hanging down here and an oxygen over in here, but that's another lecture to talk about structures. Harmaline and harmine were the earliest ones I began exploring. Harmaline itself, which is the active, or at least one of the major components of many of the plants you've been hearing about for the last 2 or 3 days. In my original experiments with that beta carboline, I got to 200 or 300 milligrams as what I thought was a pure chemical. And I got into very strange, nauseous, vomiting things. And it's a case of having nauseous and having diarrhea. And thanking the Lord, they're not quite simultaneous. It was a difficult experience. But I did try my best to visualize something, and I got my eyes closed, and I came back from the toilet and kept my eyes closed, and I had to go again, came back, and I got eyes, I got a face, I've got a mouth. I was visualizing a face that's going to be informative, and I got around to the nose, and the nose came in upside down. And there's no way I could identify the person. I gave up the whole thing, went and vomited again, and gave up on beta carbolines as entities unto themselves. As enzyme inhibitors, of course, their action is legion, and this is an area of very, very extensive research right now that is going on finding the balance between monoamine oxidase inhibition, which are things that prevent the metabolic disposition of compounds otherwise orally inactive, such as DMT, which has been talked about several times in the last 2 or 3 days, and making them orally active. Okay, and, I was saying about harmaline, which I thought was pure. It came in a bottle from Merck. An old bottle, roughly 1920-something or other, and it was a great big 100-gram bottle of harmaline that I used for all of my early work. I made it available to several other people for clinical studies. And then I got into an interesting dialogue with someone in Sweden on the purity of these materials, and I looked at that material by mass spec, and there's about 30% harmine. So this is from Merck. It says on the bottle, harmaline hydrochloride with the smells of medical authority, and yet it's converted, or it is 30% contaminated with harmine. I wrote to Merck, And I asked what kind of criterion they used back in the 20s to establish identity of materials. They answered a very nice letter saying that they have never offered this commercially, which is a nice answer, but not the answer to my question. And I got no satisfaction from there. I began playing around with it. The argument has been brought out, for example, some of the work by Boo Homestead on some of the old fractions from harmine or harmaline plants, the Banisteriopsis group, suspecting that they may oxidize spontaneously from harmaline to harmine over time, storage, period of time. I can't tell whether my material is contaminated by its being 50, 75 years old, or whether it is impure to start with. I cannot answer the question. I isolated both and purified both harmine and harmaline, and I put them aside in the same way, and they appear to be stable. Answers, I don't know, but it was a fascinating problem. Some of the published literature on the action of harmaline in clinical trials, I must say, is contaminated because the material, I won't go into who or what, was 20 or 30% harmine. I was at fault there. I gave the material to the researchers with the belief that the label was to be believed, and I now will not make that mistake again. Okay, so this gets back to where I want to go. What I think I will do, I'll put up the next one and see if I can jockey it on stage and then ignore it for a while. You move to the right and the thing moves to the left. There we are. Whoops, more or less, that's good enough. I want to get into actually the topic of my talk, which I'm about ready to start now. I've made 3 false starts, and I'll run out of time. This happened before. I go through a lecture, and by the time I'm about ready to start the lecture, I'm out of time, so I have to... I want to talk about psychoactive cacti, possibly about psychoactive poppies, and the whole area of cactus and poppies immediately brings out often a prejudiced gut response, a sort of a immediate reply. You hear, psychoactive cactus? Oh, sure. Peyote, of course, Trichocereus, that and the other, contain mescaline. What else is new? And they drop the whole topic right there. Poppies, psychoactive poppies. Oh, yes, Pepperacea, what do you call it? Opium. Opium. There's where the active compounds is. What else is new? As if all of cactus could be explained by mescaline. Forget the rest. There's nothing else. All the poppies could be explained by opium. Forget it. There's nothing else. And there's nothing can be further from the truth. These plant, the plant area, the cactaceae, are absolutely incredibly loaded, largely with those, I don't have the examples up there, tetrahydroisoquinolines, dihydroisoquinolines, isoquinolines, quaternary salts of isoquinolines. The poppy world, and not just poppy, you get off into the other related genera, but all basically I lump them together as poppies, are loaded, but they are loaded with different isoquinolines. And what I found in snooping around in the literature, that there is an extraordinary absence of overlap between the two groups. And here, that caught my fancy. In the theological sense, are there two gods, a poppy god who made the poppies and a cactus god who made the cactus, and they don't talk? Or is it one god had a little omission of attention for a while and forgot that he put beautiful techniques in one plant, other techniques in the other plant, but never cross-contaminated the techniques? So what I did, and this is exactly where, this is the arrow. This is my arrow. I'm not the bee. People said, what do you want to talk about? What have you found out recently? That's bee. I'm not talking about it. I'm talking about the arrow, how I'm going to find a bee without knowing where or what bee is. So I have this thing up here. Aha. I drew 4 tetrahydroisoquinolines and 4 more over here. This is a clutch of 8, which I'm using as my template to begin finding out where I am, what's going to happen. Here are the dimethoxy, 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 dimethoxy. The same over here, identical, except methylene dioxys in each of the 4 positions. Here I have these two. There. These 2 positions, there and there. HH, H-methyl, methyl-H, methyl-methyl. So these are all possible permutations of methylated dimethoxy with its positions being respected, tetraisoquinolines there, and the exact counterparts over here with the methylene dioxy. So what I'm arguing here is, what is the difference in the plant world, in the pharmacological world, between dimethoxy and methylene dioxy with a scattering of methyls? In the phenethylamine, the dimethoxy almost always exceeds the dimethoxy in potency or in activity, or is active whereas the other is not. 3,4 methylene dioxy amphetamine is MDA. The corresponding dimethoxy is 3,4-dimethoxy amphetamine is not active. In the case of the mescaline-like things, the poppy plant very nicely plops methylene doxys in places of 2-methoxys, forming lefauverine, for example, out of what would be otherwise mescaline. And you have materials that should be active, but no one's gotten around to explore them yet. The unexplored alkaloids in the peyote plant alone is a lifetime search. If you really want to get into some fascinating chemistry and totally unknown pharmacology, is peyote pharmacologically similar to mescaline, the mescaline to peyote? The studies have never been made. The people on which mescaline has been titrated clinically have never been given peyote as a control, and people out in the field who work with peyote have never been given mescaline as a control. Just the comparison of a cactus and the major component of the cactus would be a fabulous clinical study, as yet undone. It should be done. Okay, this top one, helenamine, is found in 6 different cactus species. It's never been found in a poppy. If you take away and begin hydrogenating the ring on the right with the points without the double bonds, you can put 1 or 2 double bonds in there. You get dihydroisoquinolines or just isoquinolines. There are a number of these known, and you go up to about 12 different cactus species in which those are found. Not one of them is found in a poppy. So they're all cactus. The next one, the N-methyl heliamine, is known in 6 cactus species. By the way, it's rather a potent monoamine oxidase inhibitor. The cacti, and I'll bring this point in a little later, are loaded with monoamine oxidase inhibitors, which it brings in the smell of what will be eventually kind of an ayahuasca direction. It is known in a number of cactus, but never in a poppy. Interestingly enough, for those who are in the analytical game, this particular compound, the methyl group there, in certain forms of analysis, certain types of mass spec analysis, comes up with this compound with a methyl group down here. Namely, that methyl group moves from there to there in the course of analysis. So you have to be a little careful, and some of the literature statements of what are in these poppies may be faulted by this internal rearrangement that is chemically bizarre and has never been studied, but has been mentioned by 2 people, and I suspect is to be respected. Salsaladine is the same world, dimethoxy, both the methyl group down here. This is an interesting material. It's found, by the way, in 6 different cacti and has never been found in a poppy. But these little groups in here, if you take these groups off, you have a material that is a dihydroxy salsalinol, which is a dihydroxymethyl H. This is a material that comes from dopamine. If you look at that dihydroxy in the amine group, it is dopamine, and if you put acetaldehyde in down here, you get that methyl group. This material has been found in chronic alcoholics as a material that is present in various parts of the body. Maybe the alcohol oxidizes to acetaldehyde and it's captured by dopamine. Dopamine, however, has also been used in the treatment of various things like Parkinsonism, and that people who are Parkinsonism positive and have this material, have this compound dihydroxy, it's called salsalinol, or sal in the medical slang, as a major component in their brain, different parts of the brain. If you find and put that in the brain of an animal, the animal becomes Parkinson-like in its behavior. So again, you have a very interesting, this would be an example of an alkaloid that's found in mammals and found in man, but is tied in with either alcohol, acetaldehyde, or dopamine, dopamine being natural, but dopamine also being given as the hydroxydopa or dopa itself as a treatment for Parkinsonism. So again, this is a tie-in together. I don't know how it's all going to fit, but this material is found in the mammalian world. The compound carnogene down at the bottom, or pectinine, has a various number of names, is again found in 3 different cacti, never found in poppies. One thing the poppy can do, it can put stuff down here. It sometimes does and sometimes doesn't. There we go, it does. Instead of this methyl group, you put big benzyl groups. You put isofuranol groups or things down in that area. These are made in buckets by the poppy world. The cactus doesn't know how to put a big thing down there. The poppy doesn't know how to get there without putting a big thing down there. So just that one little spot, that one little group down there, the methyl is cactus, big stuff down there, like a benzyl, is poppy, and no overlap. This, to me, is totally fascinating. This left-hand side is, in essence, a cactus world. Now, on the other side, methylene doxys, you say, well, gee, obviously, these are all from plant sources. But interestingly enough, the first of these, I call it MDHH4 because it's methylene doxy and has hydrogen, and it's an arbitrary, these will change, these are unpronounceable. is not found in any plant. It does not exist in any plant. The second one, the hydrohydrastinine, is found not in poppies, but is found as a product of the workup of poppies. It can be generated synthetically from certain poppy alkaloids, but again, usually with something big hanging down that in the lower one position that is dropped off. But it is on the edge of being natural, and it is on the edge of being in the poppy world. The last two over here, with a methyl H, MH, and MM, are not known in any plant at all. The methylene doxy is not a stranger to the peyote plant, but the peyote plant, or the other cacti, put it in this position. It knows how to put a methylene doxy group into a tetraisoquinoline, but it doesn't know how to get it in the 6-7 position. It only gets it in the 7-8 position. So the machinery is there in the cactus. It's just misapplied in some way. If you apply it correctly, in my opinion, and get these kind of things, you have materials that don't occur in any plant source. So this is exactly where I am. I don't know where it's going to go. I'm beginning to explore it. Some isomers of carnogene, of salsalidine, are pretty good monoamine oxidase inhibitors. Not up to the harmine area by a factor of perhaps 40, but they are there, and I think structural variations of them might indeed bring them into some sort of understanding. What I want to do, I'm going to finish completing synthesizing all these routes. These last two over here have only been in the literature 2 or 3 times as chemical intermediates for something. Never been looked for, never been found anyway in plants. These are totally strange. So I want to get these 8 compounds, and I've already made arrangements to do the work, and but add to that collection of 8 a sample of harmine and harmaline, and let the 10 of those go, this is one of my major projects right now, into analysis for monoamine oxidase inhibition. Are any of those inhibitors? I know some already are. How do they compare with harmine and harmaline, which are more or less the standards in the psychedelic industry? How do they compare? And when you find this and maybe that might be very interesting, and then I want to take off the hydrogens, make them dihydros, make them aromatic, make them with N-methyls, make them with different substituents, but take the most interesting and expand from those until you get a new collection of activity. Take the most interesting and expand from that until you get yet a newer collection of activity. Keep moving all the time from the most interesting leads to where it might go. Don't try to predict where it's going to go. Just learn from how it goes. I mentioned the and how there's anhalamine, anhalanine, anhalanidine, peyotine, lefofurine. These are all alkaloids from the cactus world. They're not just in peyote, they're in many cacti. Probably the 5 or 6 with the peo prefix and with a lofo prefix, which are named from the peyote plant, are found in perhaps 20 or 25 cactus species. They're very widely distributed in nature. But none of these dimethoxyhydroxy or trimethoxy tetrahydroisoquinolines has ever been reported in any other plant than a cactus. As I mentioned, the ones with the methylene doxy down in that bottom position are in the cactus and in other plants. You find them in a variety of other genera, in fact in other families, but not in the cactus. So with that in mind, there's one other point. I should have brought, I don't even know when I started, so what time it is now doesn't make any difference. I have one last of this. That one last is always a nice thing when people are in the audience wondering when this is going to end. My last slide brings up one other point that compares poppies in some ways and cacti. Top is dimethoxy phenethylamine with an NN dimethyl. This is very, very frequently encountered in the cactus world. The free amino NH2 dimethioxyphenethylamine, which is not an active compound, is in about over 20 cactus species. The monomethyl, which is the one with just one methyl on the far end up there, is in well over 20 cactus species. The dimethyl is known in 6. There are probably many, but at least 6 have been reported in the literature. 7, I found one in the Pachycerus, so there are 7 in which I can find that. This compound, I think, should be psychoactive. It's got all the goodies and the smells of being psychoactive. 2-methoxy groups, well, maybe it'd be better. It's methylene doxy, but why not it? The dimethyl up there, it's in many cacti, but it's never been tried in man. That compound's totally unknown in man. And I wonder if with the monoamine oxidase inhibitor, it might become orally active in man. But to me, even more intriguing is the lower compound, which uses that methylene doxy group. Here is something that is unknown in the plant world. It should be there, and it's not there. And I think, as I say, some divine mischief is going on to leave it out. It's simply made, very simply. I've made it. You make 2 steps. You make the damn thing. But it's not not in the plant world. It's almost not in the literature. Almost no mention of it in the literature. Simply made and totally unexplored. So this is kind of where I want to go. Now, where I want to go is the B. This is how I'm going to get to wherever it is I end up getting to the process. Is I want to look at these 8 compounds on the previous slide and harmine as monoamine oxidase inhibitors. Not that I particularly want it, but by looking for these, one gets into a very, oh, by the way, I didn't mention, but one of the compounds on the right, the one with the methyl down and the hydrogen out and methylene doxy, I already found is active between 50 and 100 milligrams. So there is activity to be found in these things. Anyway, I want to eventually explore all of these. It is always nice from an ethical and legal point of view, looking at things that might or might not have monoamine oxidase inhibition, in that if they are clinically active, they might be or they might not be antidepressants. And antidepressants in no way compromises any research work because it is only illegal to look for psychedelics, which I do not look for. I look for antidepressants. And this takes care very nicely of some aspects of legal morality. I want to look at these. This is kind of where I am. This is the shape of the arrow, A to B arrow right now. I want to look at these 8 compounds and harmine as monoamine oxidase inhibitors as clues to where enzymatic and biological activity might lie. And I don't know where I'm going to find the most. They've never been compared with one another. About 4 of them have been run, 3 on one system, 2 on another system. Results cannot be compared. I want all 10 on the same system so the results are directly comparable to one another. They can be compared and evaluated. I want very much to explore these materials pharmacologically, and I will continue doing what I am already doing. I think a lot of these things can be dehydrogenated to the totally aromatic dehydro N-methylquatylated. I think, for example, an area of chemical modification, ballad I can show it on this, where you have 2 methoxy groups in a row, take one of them off. You have methoxyhydroxy, this area of vanillin, isovanillin, the hydroxymethoxy metabolites of epinephrine, norepinephrine, all these goodies, lie in this general area. But one says, well, the hydroxy group has to be on the molecule so it'll get into the brain. But if the hydroxy has to be off, you can't have a bare hydroxy. But the hydroxy is next to a methoxy, it's not bare. It's compromised. And there are things that contain free hydroxy groups that do get in the brain if they are protected from getting too associated with water. An example is psilocin. Psilocin has a bare hydroxy group, yet it's active as such orally. But it is associated with a very strong base. And so you have an internal salt. And that salt may be what protects it. The same thing is totally doable in the area of the tetrahydroisoquinolines. And one last point I want to pursue is a concept that's brought out in discussions of ayahuasca, in which you might have materials such as these that should be active and would be active if they're not deaminated. And a cactus, these are the upper ones at least from a cactus, and cactus components that themselves may not be active but may inhibit that deamination. So it's exactly the parallel to ayahuasca that is very possible in a cactus. You could have a phenethylamine that would not normally be active, but it is active because in the same cactus there happens to be a tetrahydroisoquinoline that inhibits the inactivation of the phenethylamine. So in essence, you have an internal ayahuasca. This is a doable thing, a believable thing. And what is very provocative is that if you had that combination in there, you have a mixture of compounds that may show activity, but neither one of the compounds alone would show any activity. So it's an example of search for what is in a cactus, find out something in there, is it active, and fail to find activity is not necessarily a discouragement, because it may be only in combination that it's active. Therefore, the plant may be active, but the components of the plant are not. So this is kind of what I wanted to do. I wanted to bring you a report of what's going on, not where it's going to go. I don't know where it's going to go, but how I'm going to explore getting to wherever it's going to go, and let that be kind of the bottom line to the title of the talk. And I really do believe that this whole process of getting to a target rather than achieving a target is a lot more exciting. Thank you very much.
I think we have time for questions a little bit, and Dr. Shulgin would be happy to answer them.
Try to answer them. Yeah.
From the microphone, please.
Sorry, I'm too short. My brief statement is that you've certainly given me a new dimension to think about in Island by Huxley, the fact that he named one of the characters Joe Aldehyde, because I was only familiar with it in the perfume industry. I had never thought of him related to psychoactive chemicals. But my question is, I know my field is more inorganic chemistry, my interest, but with cannabis, in the US generally, it's thought that the THC is the only active compound in cannabis, and I was wondering, have there been any studies to find, there's what, 200-something other alkaloids in cannabis, and it's been proven that marinol, the isolated, doesn't work as well. Has anybody done any research on all these other ones?
Okay, let me go back kind of in the middle of the question back toward the first. One thing you termed alkaloids, be cautious, they're not alkaloids in cannabis. It is an alkaloidless plant, at least from the point of view of its activity. These materials are hydrocarbon, they're actually ethers, and they're terpene-like, but they are not alkaloids. Is THC the only active compound? Absolutely not. There are other materials in there that are known to be active, but the clinical studies in man have not, to a large measure, been successfully done.
Yeah, that's my question is.
Yeah, they're in animals, yes. And there's no question but what they will contribute, in my mind, at one level or another, to the overall action of the plant. To study the action of THC in isolation is a very unnatural thing to do. THC of marinol is actually synthesized. It doesn't come from the plant, although there's work in Holland in obtaining it from the plant in a competitive way.
Isn't it even hexahydrocannabinol? It's a separate...
Sorry?
It's hexahydrocannabinol, right? It's a separate...
Well, the tetrahydro it has one double bond. The hexahydro has been studied in animals. I don't remember the results of the study. I don't believe it's found in the plant. But there are many variations of the double bond position and variations of the ring integrity that are common components of the plant. And many have been studied in animal studies. I do not know of clinical studies in man.
Okay. Well, you keep working on cactus and poppies and all. Work on this.
Good. Is there a microphone? Both? Good. Good. I thank you very, very much.
Look at these. Wait a minute. Is this what you were up to? Arts and crafts. This is fabulous. Look at that face. Come on, is that a great face or what? That's Michael Jackson before and after.
I've never had surgery. Never, ever.
You have a look like a deer in front of a Peterbilt. Kind of... Hit the brakes, Al. Hit the brakes. I love this one. This is a very attractive one. This one should go on the cover of Sports Illustrated. Not the swimsuit issue, but the boxing.
I should have never gotten in the ring, but I will take him in 3 rounds. I want the belt to go with my purse.
You're a ding...